Hi, everyone. Welcome back to the sleepy post-lunch session. It's a pleasure to have Moshe. Moshe is a postdoctoral scholar working with Professor Carola Vivian Schonle. His interests are in graphical architectures, deep learning, and inverse problems. So today he's going to talk about a graph learning perspective on quadratic binary optimization.
Okay. So I hope you can all hear me. Thank you for inviting me. I thank Pietro and Tianzi and Challenger for organizing this. Let's see what we'll talk about today. So we'll talk a little bit on solving NP-hard optimization problems. Specifically, we'll focus on the quadratic unconstrained binary optimization, or in short, QUBO. And we'll show how we aim to replace optimization with learning. We'll show a little bit of analysis of the problem that we consider and the architectures that we look at. We will also talk about how to actually train these things, because that's not a trivial thing in itself, I would say. And some results for this paper that we published. So this is based on a paper that I published together with Professor Eldad Aber from UBC. And now I also work with Simon, who is here, on continuing this project. So NP-hard problems, I assume that all of us know what they are, but basically it is a class of problems that are at least as hard as the hardest problems in NP, which is a non-deterministic polynomial time problems. And the characteristic is that a problem that we denote by H, I see that someone is in the waiting room, so I'll admit them. Yeah? Okay. A problem H is NP-hard if every other problem in NP can be reduced in polynomial time to H. So what is the implication of that? It's that we can solving any NP-hard problem in polynomial time, if we could do it, would solve all the NP problems in polynomial time, because we can have this reduction. Now, let's talk a little bit about the practice or practicality of NP-hard problems. So obviously we cannot solve them exactly in polynomial time, but many times we can get quite good approximations to their solutions in polynomial times using different algorithms and approximation algorithms. But there are also other problems that are very hard to solve. And the reality is that we use them every day. So, whether it is when we try to navigate, when we try to build some schedule. I mean, you have to schedule this thing, right? This is not an easy problem in investing. So when we want to optimize a portfolio and so on and so on. And maybe I think that many people in the crowd here were traveling to get here. So you had to pack your bag, and you had, usually you have some budget. So you have some space in your bag, and you need to decide what are you going to pack while maximizing your utility function. So I think this is like a very motivating example for why we would want to have a way to solve these problems in an easy way. And specifically, what we consider in this work is the QUBO problem, or quadratic unconstrained binary optimization problem. So I think at a first glance, it looks very simple. I mean, we just have a quadratic function, so why is it so hard to optimize it? So the problem is that here we are not interested in X that is continuous, but rather we want a binary solution. So this is an NP-hard problem, but this problem is actually apparent in many real-world applications, although it looks very simple. For example, in quantum computing, and there are many heuristics for solving or for approximating a solution for this problem. Now, there are many popular heuristic-based algorithms. Mostly of them are based on search. So we do have, for example, there is taboo search, which is basically kind of like a greedy algorithm where we try to look for some perturbation in our solution. Then we evaluate what is the what is the cost, so what is the value of the function, and then according to that and a few more rules, we try to get to a solution. It's actually not bad. It's used quite a lot. So it looks like this. So basically, we would start from some solution, and then we would track all of the previous states we visited. So this is basically, just like a quick introduction to taboo search. Now, the thing with NP hard problems is that, all of these algorithms, essentially, or most of them, try to find an approximation from scratch, right? So we are given a problem, and then we say, now let's try to approximate a solution. But what we asked ourselves in this work, in this project, is do we actually have to do that? So instead of solving from scratch every time, can we actually try to learn a neural network that will allow us to approximate a solution? And I think that, when we think about this in real life, let's say with navigation or building some schedule, when we need to navigate and the conditions change a little bit, or when we need to build some schedule, we do have some prior, right? So we know roughly where we should go, where we shouldn't go, who do we want to schedule at different times, and so on. And we almost never start from scratch, right? So when we see a slightly different condition, we are not going to just resolve everything from scratch. So, and this is basically this prior idea that we wanted to see if we can actually learn. So, so what do we actually want to do? So we want to learn a map Q that, given some condition B, and for this exercise, or for this project, we consider a fixed matrix A. We'll talk about this later. But given this vector B, and parameterized by parameters theta that are learnable, can we learn this map that will take us into the solution, or will approximate the solution, right? So the question, first is, can we actually learn such a thing? Obviously we can go ahead and try, but first we wanted to really think and see if we can characterize this map and see if we have any chance in at least hoping that we can do that. So, what we say is that similar to many different things that you want to learn is that if this map is smooth enough, then we have a good chance of learning it. So what we did in the paper, we analyzed the sensitivity of the problem. So basically the sensitivity of the solution as we change B. So again, we fix A in this case, and indeed it is a restricted case, but it's actually very useful, especially in quantum computing. And what we did is that we had some analysis of the sensitivity of this problem. And what we found, very briefly, is that the QUBO problem at its optimum, so if we are at its optimum given some given problem, it is piecewise differentiable with respect to the vector B, and it's also going to be piecewise smooth. So we characterize this, like in the paper. I think that something broke a little bit with the equation over there, but we also wanted to see it for some specific problem. So what we did is that we initialized some random problem. In this case, it was on a grid. And then what we did is we defined the function x of st. So what we did is that we took two random orthogonal directions, which are perturbation vectors. And now we can control and play with S and T, which are the coefficients that tell us how far do we actually move from the optimum of a given problem. And then what we did is that we were plotting the solution distance, right? So if we take x at 0, 0, it means that we are actually staying at the original problem, right? Because now what we did is that we changed our problem. It should be, I think, transpose. So I don't know what happened here. But anyway, yeah. So basically, what we see is that if we are going to perturb our problem, right, so S&T will control how much we are changing our problem, then you can see it's the plots on the right for several cases, so for several instances of the problem. So really what you see is that this map is smooth. So this gives us hope and some intuition that we can actually learn such a thing, because if this map was very, I think for people that know graphs here, heterophilic, so if it was very non-smooth, if it was going to change quite a lot, then this map will be very, very challenging to learn. So with that in hand, we also wanted to try and understand what the solution actually looks like. So notice that what I'm referring to here is the sensitivity of the problem as I'm changing its parameters, right? So, but this doesn't tell me what the typical solution looks like. It only says, it only tells us that the problem will be stable when I change it. So then, what we've done is that we said, wait, we have this matrix A, all right, and we have this vector B. So you will see in a second that this actually really fits into node classification with GNNs, this setting. If we are going to treat A as our graph, I think that actually a nice thing here, and this is maybe more, like a general thing that would be interesting for graph learning people, is that usually we are used to transductive learning on graphs, right? So like when we do node classification. So we get a graph like Cora, and then we get some of the nodes are labeled, and we try to predict the labels of the rest of the nodes. Actually, the nice thing here is that in this problem, it is fully inductive because we are generating a lot of different problems. And when we try to predict the solution, we do not assume that we know a partial solution. So you will see it in a second, but just as a heads up, I think it's very interesting and could be taken further. So, and then, when we looked at the typical solutions of such problems, which you can see on a grid here, what we see is that this solution looks quite heterophilic, right? So what is heterophilic and homophilic? So this is quite a well-known term in graph learning, but basically homophilic means that neighboring nodes have similar labels or similar features, depending on what we look at. And heterophilic means that they are actually quite different. So, upon inspecting the solutions that we see for different QUBO problems, and this is also quite known from literature, you see that actually the solution is heterophilic. So with that, we said, okay, now we can actually try to learn this thing with a GNN, which we will talk about in a second. And in our setting, A is going to be basically the adjacency matrix. B is going to be my nodal data, so basically my node features. And X, which is actually the solution of QUBO, is going to be what I'm trying to predict. And in our case, it even fits very nicely into the node classification problem because we actually try to predict a binary label. So, okay. So now the question, before this question, so let's first actually describe the architecture that we are using. So in practice, this problem can be, or at least we can try to solve it with any GNN. But because we know that the solution looks heterophilic, we chose to use something that will allow us to model heterophilic behavior. And in addition, what we did is that we also added problem-aware features. So recall again what our problem looks like. So basically, it looks nothing but like the equation that you see here, right? This is the quadratic form. So if instead of X, we were to replace it with our features and augment our network with these features, we basically get almost like a reading of the internal of the network or the internal neural solution of our problem so that the network can use it. And we'll see soon how useful is that. And so what does our network look like overall? So I think basically like almost any GNN that you can think of. So we get some features, which are B. We embed them with an encoder. Then we compute the QUBO-aware features that I just described, and then we use a GNN. Now, for the GNN, we could have technically, as I said, use any GNN, but specifically, well, we are biased because we had published work on reaction diffusion GNNs, but I think also because the Ising problem, which can be modeled with reaction and diffusion, is a specific case of QUBO. So for us, it was very natural to do it, and I'll show you comparisons with different architectures. And of course, in the end, we will have some final classifier. So it seems like we are done, right? Like now we have this formulation, we can run it, get some results, and that's it, right? So what's missing? Exactly. So how are we going to get supervision? Because we need pairs. I mean, we want to get some XP, but how are we going to backpropagate? Like, what are we going to supervise it with? So indeed, this is a very hard problem, I think, for any network where you try to feed such data that is very hard to acquire. So instead, what we found useful is to actually flip the roles. So when we acquire the data. So usually you would say, well, I'll give you a problem, which is defined by A and B, and you'll find X, right? But this is very hard. I mean, if we want to even have more than 10 nodes, it's not really possible to get a proper solution. Even if we use, like some algorithm, it will be very hard. I mean, some like approximation algorithm, it will still take a lot of time. So instead, what we said is, what if we first pick X and A? I mean, this is easy, right? And then we find a B that fits to it. And we do it specifically with interior point methods. So how do we do it? So we take the problem and we relax it a bit. So we say, we use specifically here, we use a log barrier function. So we have to choose some X, which because we don't want it to explode, so we choose something between epsilon and 1 minus epsilon. And we already, this is the quite fairly known problem, so we have a closed form solution. So we can get B that actually fits this X. So let me show you a small example. So let's say that A, our matrix, looks as follows. So this is what the solution is going to look like as a function of B. Okay, so B, again, it's a vector. It's a two-dimensional vector. So you can see the solution that we are getting, and its landscape, it's a piecewise smooth landscape as we just characterized earlier. Okay, and we can also get the optimal B given some binary vector X, right? So, and then what we do actually is that we still need to be careful because we haven't really solved the original problem that we looked at. We solved some relaxation of it, right? So it could be that this B actually it will make the equation correct, but it's not really solving the original QUBO problem. So instead what we do is that after we acquire this B, using a closed form solution, we perturb it a bit. So we add some noise to it. And then we perform a few steps of taboo search, right? So what this does is that it actually brings us back into the manifold of the problem that we are trying to solve. And another thing that it does is that we can actually now use it almost as an augmentation technique. Because when we add this noise and we solve it, then we are going to explore the surface even further. So we have that. I think overall, this is what it looks like. So I think it's worth just going over it quickly. So basically, we have to pick some problem, and then like some matrix A, which again we assume that it is fixed, and we'll talk about this later. And and then we start generating pairs. So this doesn't take too long, even for large problems. So even if we try to look at graphs with like 1,000 nodes, which may sound small to you, but actually you will see soon how much time it takes to solve it with other approximators, you can get about 50,000 examples in, I think, like 10 minutes. And I think maybe Simon can approve that. since he played with this as well. So yeah, this is overall the approach, and I think it's very, very interesting, and it could be potentially also used in other projects that you may have that may involve a very complicated data acquisition process. So let's look at some results. Okay, this is quite a big table, so I'll try to go over it bit by bit. So we considered 3 different cases, from small problems to large problems. And for the small problems, we could actually solve it exhaustively, right? So we could solve the problem exhaustively and know for sure that our method works without any approximations. And let's see what we get. So obviously, if we use an exhaustive search, then we are going to get 100%. But as you can see, even if I take 256 nodes, just getting one solution exhaustively is going to take, at least on my server, on CPU, is going to take 10 to the power of 7 days. So obviously, this is not realistic, and it also shows you why you cannot acquire data in such a way. It's just not going to work. We also looked at classical solutions. So by classical, I mean the heuristic-based algorithms, that one of them which I talked about earlier, which is taboo search, and another method that is comes more from the world of quantum computing. So you can see that even these don't really give you 100% accuracy in terms of solution. And they are also quite expensive. So yeah, they are obviously it is better than 10 to the power of 7, but they also take quite a lot of time, and this is per one solution. So even if we try to generate one example, this would be, to generate examples using this algorithm from scratch, this would be very hard, and also this is why it motivates us to generate the data in the way we did. We also considered different GNNs. So starting from GCN, GAT, and GIN, which are a bit more, let's say a little bit, they would be not bad on homophilic data sets, but they are known to have shortcomings on heterophilic data sets or tasks. So hence you can see that the performance is slightly worse. And if we consider other, DIR GNN, which is a method that is actually quite good at heterophilic data sets, then the performance gets better. And let's get to our results. So what we see is that actually we get quite nice performance. It's many times very similar to the classical algorithms, but look at the time. We only need a fraction of the time. So this is already an achievement by itself. But then we said, okay, we can get to some solution. We can approximate it with the neural network and then combine it with a few more steps of taboo search. So it is quite known that with taboo search, if you are very close to the solution, then you are more likely to converge into the real one. So yeah, then what we said is, okay, we can take our solution and apply a few more. It was, in this case, I think, up to 10 iterations of taboo search. And you can see that for a little bit of added time and cost, you can improve the performance even further, both in terms of the accuracy and both in terms of the relative QUBO objective loss. So these are the results. I also promised you that I will show you that QUBO features are useful. So what you can see here is that when we actually include QUBO features, we manage to get much lower, which is better, QUBO loss. So, and I think this concept in essence can be used to any of your GNN problems. For example, you could also apply to node classification, so it can be interesting by itself. And let me conclude. So in this work, what we show is that we can actually, at least we show a first attempt from our side in replacing optimization with learning for the QUBO problem. We showed that QUBO-aware indicator features help the network. I see that help is deleted here, but it helps. And we showed a very interesting, in my opinion, approach for acquiring data. We call it self-supervised because it is self-generated. for large-scale problems that are very hard to acquire data for. For future directions, so as I told you, in this work we consider the fixed graph, but some research efforts that we are working on right now is actually in generalizing for different variable graphs. I think this would be even better, and we have some positive results. So again, thanks to Simon. And the question is also, can we solve other and harder problems, also including constraints? And I think for those that are really interested in the frontier of graph learning, you probably can see how this goes into as a good prior for graph foundation models. So I think that this is a very interesting discussion by itself. So I'll be very happy to talk about this with you offline, or if you have a question now. And thank you for listening.
Questions for Moshe?
Nice talk. About the generation of the training data, how good is the quality of the training data depending on the condition number of A? Did you try to study that?
Actually, we have not, but what I can say, so you are asking if I change A and I look at its condition number, what would the quality of the solution compare to the, so we actually have not looked at this.
Because I think the way how you generate the data can be biased according to that. Yeah.
Yes, yeah, I agree. So in this case, we used the random matrices. So we didn't really study this, but I do think that it's it's a thing that is worth investigating. One thing that we are investigating and this is in relation to generalizing to other graphs, which I think also influences this, is indeed the distribution of the graph that you are getting, which you can relate to the condition number, and see how if we can but generalize to other types of graphs, and if we can actually quantify when it should and when it shouldn't generalize. So I think that in this sense it is somewhat related to this, but we've not tried it, but I think it's very interesting.
And then also the number of samples that you need in order to achieve specific I think is also related to that.
Yes.
Now.
Yeah. So this is definitely one of the efforts that we are working on now. In this case, we used it was 50,000 examples, but the thing that is important to remember is that A was fixed, right? So but we did change B. So the problem itself does change, but you do not change the whole problem, right? So, but we do see that with preliminary results we have now, we do see that you can actually generalize depending on the graph with about 50,000 examples. You can generalize across graphs, but it will depend on the distribution. So I definitely see that you would need to, for example, looking at the condition number could be useful. We try to look at also.
Can you adapt because you are taking a grid now, if I'm not mistaken.
So we tried several things. So we took both a grid and graphs. So like let's say like motif graphs, right?
I was thinking that maybe you can follow the eigenvector directions in order to decide how to design the topology, so that you follow also the shape of the support with respect to the quadratic function.
So I'm not sure. I think that I understand like what you are saying, but I'm not sure that I understand the question. Like if you look at the
because you are sampling now. In order to have a discrete graph, you are sampling.
Yes.
And now you are sampling uniformly over the space.
Yes. Yeah.
But maybe according to the property of A, you can sample in a different way.
Oh, I see. Okay. Yes. I agree that you could do that. But on the other hand, you could also ask if this does not create bias that makes your training easier than it should be, right? So there's always this
function. Maybe you can show some prove some theorem about that.
Yes. Yeah. No, I agree. I agree that it's worth looking at this direction. We are actually, as I said, we look at this not from the perspective that you proposed, but I think it's a very interesting complementary direction to look at. Thank you.
Other questions for Moshe? Yeah, can I throw this?
Are you going to throw it all the way?
I would like to try. Okay, maybe I'll take a step first. Awesome.
Hi. Thanks for a very interesting talk. So in the table you showed some metrics, and
Yes.
I think so here, like, the primary advantage that we see is in terms of speed.
Yes.
But the accuracy for the classical algorithms and the proposed method is kind of similar or in the same ballpark. But when you say like the time in milliseconds, is it only the inference time that you're considering, or are you also considering the training time? Because you also need to train the network, and
Yes.
then you need to do the inference. But with heuristic, it's like you run the algorithm every single time, but with the network, you also have some training time before you extract the performance. So
Yes. Yeah. So thank you. This is a great question. So I would say that for small problems, you can see that the performance is quite similar. When the problems start to get higher, I would say that sometimes you can see, actually it was surprising that SAB was intuitively I expected it to be better than taboo search, but we saw that as we increase the problem size, it actually gets worse. So about the time. So by IT we mean what we meant is like what is it? It's like inference time. So it is indeed inference. It does not include the training. The good thing is that actually the training is not that expensive. So you can get you can train this thing by something like 5 to 10 minutes or something like that, and then you can just use it, right? Once you have the model, you can use it. So and on the other hand, the time that you see here is the time to actually get a prediction for one problem, right? So even when we have inference here, now if you have like a whole test set to test on this, you would have to multiply it by the number of examples, so it would become even less appealing, I would say.
Yeah,
so.
And also, like, with classical algorithms, you already kind of get some generalization guarantees because you can always analyze the algorithms, but with learning algorithms, it depends on the size of your training data. So that will also increase the training time, if you consider multiple A's. And so then the primary advantage is in terms of time then.
I would say that yes, like in the examples that we see here, this is the case. And indeed, the next steps are to actually analyze it and see if we can say something about when will it generalize and when it won't, and what is the sample complexity so that we can know how many examples you need. But I would say that this is valid for almost practically any learning mechanism, right?
So, yeah, thanks.
Thank you.
Thanks, Moshe. It seems you might have a general framework for minimizing quadratic energy functionals on graphs, especially when you make the features aligned with the problem. And then you might see like a propagation through the GNN that's like a gradient effect. Do you think this could be applied to different problems? Are you aware of any other problems in this framework?
So I would say that maybe one thing to notice here is that like slightly different than the energy we are used to look at, like when our solution can be continuous, or our features in this case, because we are in the neural space. Here the solution is actually binary, right? So it's a bit more complex. So in terms of where you can take this, so basically, I mean, because we can have a reduction from this problem to any other NPR problem. So if you have another problem, of course, you could take it over there. I can tell you that, for example, we did have like some discussions like with Amazon when they wanted to use this thing for scheduling. So as I said, like this problem can be used for if you want to do like portfolio optimization, like scheduling, routing, and so on. So this is, and it is also quite useful in drug design. At least that's what I heard. So I'm not an expert on that. So I would say that yes. But you do need to see that the solution or the type of solution that we are evolving here is a little bit different than what we are used to in, let's say, like graph neural diffusion and so on, where the solution can be continuous. So this would be maybe the only thing to. Yeah, so actually our network here was, as I said, in QUBO-GNN, the backbone of the GNN here. So I left it very abstract on purpose because, again, you could use many architectures, but we did use a reaction diffusion network, which is one of the works we did earlier, and it is a generalization of LN-CAN neural networks. So yeah, and just to add, this also makes sense because a lot of problems, for example, the Ising model can be viewed as QUBO, and so like graph reaction diffusion and LN-CAN take inspiration from Ising models and so on. So there is very nice, I would say, coupling of both the neural dynamics and the actual problem that is underlying. So, yeah.
If there are no more questions, let's thank Moshe again for your
Thank you.
I need to share the screen in Zoom. I think you need to let me in the
Challenger?
in the.
I think I just let you in.
No, I may have gotten out.
I know the host, so I don't think I have.
No, you have.
Do I have? Participants. Yes, that one.
You're co-host.
Co-host.
Should we just try again?
Let me